So here we have zero crossings indicated by our yellow zero crossing lamp over there, and the yellow lamp on the digital control module. And we'll now turn on our load, that light bulb, by pressing the load control button, like so. That can be controlled either with that or with the load control switch on the analog front end, which can either allow for control from the digital control module, forced off, or forced on, independent of the digital control module. Here we have a plot of line voltage. It's actually coming from our AC synthesizer at the moment, but you can see that as I turn off the light bulb, the voltage drop on the synthesizer goes down. When I turn on the light bulb, the voltage returns to about 118.9 volts. Here we are demonstrating our successful voltage calibration. Here we are demonstrating our capability of measuring higher voltages, including 240 volt power. And above. Here we will show the inrush current of a light bulb. Currently we are examining the noise at our input, but then we will turn the light bulb on. You'll see that there is a small spike as the filament warms up, and then its resistance increases again. Here we will turn the light bulb off again. You'll see that its current decreases. When we turn the light bulb on, we again experience that inrush current. If we turn the light bulb off and on again quickly, we have less of an inrush spike because the filament did not have time to cool off adequately. Here we are displaying the frequency we're reading back, and as we're using the synthesizer, I can change the frequency up, to 67 hertz, maybe much higher, perhaps 80 hertz. Back down to around 60 hertz. The delay is due to our linear regression used to acquire more accurate frequency information. This frequency is not coming from the line, instead it is coming from our power synthesizer, so it is being driven by a function generator currently. Here we will be demonstrating changing relay settings to vary the load. As we increase the load, these are resistors that are in phase. They're sequenced to protect the relays in their current configuration. And we can create phase shifting by adding capacitance in fine steps. The capacitance settings are shown on this breakout board, and they are sequenced to pre-charge and discharge the capacitor safely. In the capacitor control system. Now, as the resistors dissipate more power, the temperature goes up. This is in Fahrenheit. On the measured water temperature of our water cooling loop and the water cooled resistors. And as the temperature goes up, a fan controller will adjust the airflow from our fan There is a water wheel to make sure that the pump is flowing correctly and gives us information regarding water flow. That pictured center is the radiator. And as you can hear, as the temperature still climbs, the fan grows louder. We have automatic fan control so that when we're operating at lower ranges, we aren't deafened by the fan, whose maximum air movement is 460 cubic feet a minute and is quite loud. It pulls 2 amps at 24 volts. The maximum steady state temperature of the system is 160 Fahrenheit. This board coordinates the operation of the pump and the fan. The blinking light is the output from the water wheel tachometer showing water movement. All of these devices are controlled by the relay control module, which is this center card with a large D sub and a yellow blinking light. The blinking light indicates that loads are active. That D sub goes to our breakout card here, where it is connected to the resistors over the silver connector, the resistor relays. The 15-pin D sub goes to the fan controller, or the fan and pump board, and the 25-pin goes to the capacitors, the capacitor relay board, with its lid off below. Our cards in our enclosure use card extractors for ease of removal. So here is our digital control module featuring an ATSAM 4E ARM processor. Starting at the bottom right hand corner, we have our power supply, which converts our chassis voltage of 24 volts to 3.3 volts for the card with a non-isolated switching regulator. Here's a 32 kilohertz clock and 150 megahertz clock to feed the ARM processor. Here is a level shifter used for the RS-232 port. We are using a 3.5 millimeter audio jack instead of a D-sub connector for this port, as it is easier to fit on our front panel. Here is a 20-pin JTAG connector for programming our ARM processor. This is a 25 megahertz crystal to run the Ethernet PHY, connecting to this Ethernet integrated magnetics jack. And here is a USB port. The USB port has ground and V-bus coming onto our board for sensing whether or not something is connected. However, ground is protected by this fuse in case of a fault internal to our device. Here you can see all the different lines that are broken out from the processor onto the bus to communicate with our different devices. We have a variety of buttons. We have a 3-position switch, a reset button, and a button for controlling the load or other things that can illuminate either red or green, as well as the common feature among our different devices is a 3-level LED traffic light that we use for a variety of debugging purposes and for indicating current state. The digital control module is the only board used in our device that has components on the back, and this was done to ease the component density on the front when it comes to things like all of these bypass capacitors and such. Here we have the analog front end module. This module is the heart of our measurements that are taken. So we have some Nutric power con connectors, one male, one female. Power enters here and is switched by these 2 relays, which are each 30 amp relays, which is outside of our specification of measurement of 20 amps, to try and reduce inaccuracies caused by drop across those relays and to improve reliability. The current takes 2 turns through this current transformer before exiting again at the measurement output for connecting the load under test. The voltage is picked off before the relay so that the voltage of the line can be measured regardless of whether or not the load is connected. This is useful as you can determine the line impedance of the building or location where you are measuring your devices based on the voltage drop incurred per a specific load applied. The voltage that's picked off before the relays is protected by these two 62 milliamp telecom fuses that prevent any catastrophic failures of the line or extremely large surges from causing any further damage. We have 2 high stability flame-proof 1 megohm resistors that form a differential divider with these 2 1 kilo ohm resistors, which are all matched in temperature coefficient so that the error is kept within ratio with itself so that it does not amplify or attenuate our input based on temperature changes appreciably. Here we have 2 film capacitors that are used for low-pass filtering and 3 bidirectional TVSS diodes that prevent surges from damaging our device. As configured, our device can withstand a 5,000 volt surge without damage. However, that is primarily in terms of the integrity of the measurement circuit and not of our connectors, etc. Here is the heart of the measurement, the AD7753 made by Analog Devices. It is augmented by an external voltage reference to improve our accuracy and precision. And here are the filter capacitors and resistors for terminating the current transformer. The grounds on this board are split between the analog section and the digital section. In the digital section we have the crystal to run the AD7753, as well as these 2 digital isolators, which are transformer based by Analog Devices, for galvanically isolating our measurement device from the rest of the instrument, as it is not galvanically isolated from the line in the measurement section, as we're using resistors to measure the voltage, which improves our harmonic response and reduces the error and non-linearities found in transformer solutions. Here is our regulated switching supply, which produces 5 volts to run all of this, and conveniently we can use our isolators here as 5 volt to 3.3 volt converters, as our bus runs at 3.3 volts just as the digital control module does. Here we have a 4000 series logic part which picks the interrupt used in the card based on an address. Likewise, this jumper performs the same task. All of the devices in the chassis are protected by polyfuses. Here is one for this device. This is the 3.3 volt regulator for powering the isolators, and here's a temperature sensor that could be used for further characterizing the device across temperature if further calibration was pursued. Here we have a 4000 series counter which divides down the line so that you get blinks at 2 Hertz whenever you have 0 crossings at the input. A switch for controlling the operation of the relays, whether or not they are controlled by the digital control module, overridden on this device itself or forced off, and a BNC connector for picking off a 0 crossing signal for debugging, testing, and synchronization purposes. This board does not have any components on the back. However, viewing the back of the board does allow the ground planes to be seen. It, like every other board other than the digital control module, is only a 2-layer circuit board, and here you can see the analog ground and the digital ground, which are connected in one place through this filter, ferrite filter. Wide isolation distances, following recommendations from UL for an uncontaminated environment, were used to maintain at least 2500 volts of isolation, which follows the specification of our switching converter and our digital isolators. This is to prevent problems in case of lightning-induced surges or other such events. Here we have the relay control module, critical for enabling our calibration of the device. It has a variety of fairly unique features compared to the others and is both simpler and much more complex in certain ways. Here we have the same DIN backplane connector, but there are 2 glass fuses, and these fuses lift both ground and the 24-volt power rail and are used to protect the device in case of a fault within any of the controlled relay loads, based on a variety of experiences we had last semester. This is a CPLD. It is used to sequence the capacitors as well as provide a variety of other functions. Here are two SPI-based inductive load drivers by Infineon. We use them to drive the relays for the resistor load, and also could use them for driving other loads. This bundle of transistors is to replace the ULN 2003 drivers, as they did not perform to specification when it came to their standoff voltage and inductive kickback protection. And this was the most easily expedited solution to our problem when it came to time constraints. However, further testing of the ULN 2003 is desired after the completion of the semester. Here's a MAX 6615 fan controller. This fan controller both controls the fan for the resistive water-cooled load and receives tachometer information from the paddle wheel sensor, Hall effect paddle wheel sensor in the water-cooled load, so that we can determine if the pump is stalled. This is another BNC connector, except it is used as an input for an emergency stop, which disconnects the loads. Here again is a traffic light LED to demonstrate state. And here is a metal oxide varistor and a very large TVSS diode to protect the switch 24-volt line that is interrupted by the e-stop from transients from the relays and other loads. It's also protected by a polyfuse here in yellow. There's a 5-volt regulator as well for providing 5 volts to any auxiliary loads on the HD44 load connector. It was difficult to determine what kind of connector should be used here because we kept trying different sizes and trying to get a balance between what we could fit on the card with something else and not having too many pins left over. Ultimately, doing this again, I would have used a non-high density connector, as routing through the high density pins was challenging. This board has a lot of protection on it, and that's because it interfaces with external loads and devices that may experience short circuits or other strange transients, and that is why, in fact, it has 1, 2, 3, 4, 5, 6, 7 fuses. And this device with a yellow back here is a DC solid-state relay, which is used to switch the switch 24 bus. The switch 24 bus has to be far more robust than originally expected, not only because of the many relay loads switched upon it, but our greatest load in the entire device, and actually what determines the rating of the chassis power supply, is the fan that we use to cool the water-cooled load, which is an extremely powerful fan and pulls 2 amps at maximum throttle, which is part of the reason why we like to throttle it down when that is unnecessary. It also saves our hearing. Here you see another 3.3 volt switcher brick, just like the one in the digital control module. We reused a lot of similar parts within the design to try and cut down on the distinct parts in our bill of materials. The bill of materials in this project was extremely large, and managing it was one of the greatest challenges.